So in this video, we are going to look at using matrices to solve simultaneous equations. So consider the pair of simultaneous equations 3x minus 6y equals to 24 and 2x plus y is equals to 1. Now, the usual methods for solving these simultaneous equations are either by elimination or the substitution method. That will be discussed in our upcoming video, but we're going to look at the matrix method. So in order to do this, we do the following steps. We look at the coefficients of the variables in both equations and put that in a matrix called the matrix of coefficients. So we form the matrix of coefficients. So the coefficient of the x term in the first equation, called equation 1, called equation 2, is 3, the y is 6 minus 6. In the second equation is 2, and in front of the y the coefficient is 1. Now we put our column vector of variables, which is just x and y. Now an interesting thing to note is that all column vectors or all vectors are matrices, but not all matrices are vectors. That's just something interesting. Ponder that statement. So here we have a matrix of 2 by 1. Here's a 2 by 2. So it is commutable, and we equal it to whatever our constants, our column vector of constants, so 24 and 1. So let's put some notation to this. If this is A, let's call this B, and here is C. So we have basically A, matrix A times B equals to C. We want to find the solution for matrix B. So if we multiply both sides by the inverse of A, we would get A inverse by A B, which is equals to A inverse by C. Now A inverse by A gives you the identity. Now the identity is a matrix. The identity is a matrix, namely the identity of a 2 by matrix. 2 by 2 matrix is this matrix, and it's basically the matrix analogy of multiplied by 1, meaning any matrix by the identity is equals to the identity times that matrix, which is equals to that matrix. What this is saying is, if you take a matrix and multiply by the identity, you would get back the original matrix. Kind of like if you take any number and multiply it by 1, you would get back the original number. So the identity matrix times B is just B, which is A inverse by C, A inverse by C. So the identity matrix by B is just B, which is A inverse C. So this is equivalent to saying that xy would be given by A inverse times 24 and 1. So we need to find A inverse. So making some, okay, I'm carrying this working over here. So A inverse, recall the formula, 1 all over the determinant, which is AD minus BC by the adjoint of E. So the adjoint of E. So A inverse is 1 all over 3 by 1 is 3, minus 6 by 2 is minus 12. 3 minus minus 12 is 15. And the adjoint, swap 3 and 1, you would get 1 and 3, and here would be 6 and negative 2. So this is the inverse of E here. So now we have x, y is equals to 1 on 15 by 1, 6, negative 2, 3 by 24 and 1. So is this commutable? Yes, it is. So carrying this up here, get x, y is equals to 1 on 15. Now row by column. So we get row 1 by this column, so 1 by 24. It's 24 plus 6 by 1 is just 6. 24 plus 6 is 30. 30. And now this row by this column, minus 2 by 24 is minus 48, plus 3 by 1 is 3, minus 48 plus 3. Minus 48 plus 3 is minus 45. Now we get xy is equals the scalar multiplication 30 all over minus 15 and 45 all over minus 15. Sorry, 15. Why did I get there? Yeah, not so this is positive 15. Here where the minus 45 is. Positive 15, so 1, 3, 1, 2. So we get x, y is equals to 2 and negative 3. Done. We could test this by substituting into our original equation. So when x is 2, we would get 2 by 2, which is 4, plus minus 3 is 4 minus 3, which is 1. So correct.